Hello, everyone. Welcome to Discrete Math. Sorry about the delay. When your boss says, "Oh, we need to meet," all right, you can meet at 3. Your class doesn't start till 3:30. I'm like, I gotta do stuff. Blah 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 blah. 3:30 is rolling around. You can meet all the way till 3:30. No, I have to set up the screen. I have to do all the preps. And it's your boss, right? So you can't say, "Go away." So sorry about that. It's disrespectful for me to be so late. Let's see here. I've got OBS working. You guys see a black screen, which is perfect. So that's working. Let's see if this will work now. So this has to be up. All right. Okay, so let's go over the quiz. Everybody wants to know about the quiz. So I've got the quiz up. I've got this weird thing up that needs to go away. And then there it is. Okay, so let's look at this quiz. The idea here is what's going to happen here. So let's look at the numbers, okay? So Alice and Bob agree to use P equals 11 and G equals 7. Okay? So both of those things are public information, right? Public. P equals 11, that's our prime, G equals 7. Now, Alice sent Bob 3. So when the algorithm happens, right, Alice chooses A. Private. And then computes the base, which was 7. Computes G to the A mod 11. And that number equals big A. Now, big A is something that went over the network. So big A here equals 3. At the same time, Bob chooses little b and computes G to the little b mod 11. And that's going to equal big B, and that's going to go over the network. All right, so 1 to 5, how do we feel about what's about to happen here? What's going on? Who's sending what over the network? Right? So these are all public information. Okay. So, the question is, what happened here? The question is, what happened here? So, I know that G, which is 7 to the A mod 11 equaled 3. And 7 to the B mod 11 equaled 5. Okay? So now the question is, how did I get those numbers? Well, let's look at the chart. I have this helpful chart. I've got 7 to the A mod 11. By the way, in PHP, when you do the, you guys figured this out, but the way you would write 7 to the A in PHP, this is just a slight note, is 7 to is star star. That double star means do an exponent. And the reason why the chart had that on Canvas was because I was using that program to generate those charts. All right, so 7 to the A mod 11 equals 3. So let's see. Not that one, not that one. That one's going to be that row. So 7 to the B mod 11 equals 5. That's that row. Equals 2 equaled 3. That's that row. So how do we feel about that 1 to 5? Which rows I need to solve this problem? Right, so yes. So in other words, I'm solving everything mod 11 here, and I could break up things mod 11. But the point is that you saw that there were like, so which ones do I have to generate, right? Which tables do I have to generate? I have to generate one. I don't need to generate to the 0, right? That's easy. I don't need to generate the table for base of 1, right? So base of 0 is always going to give me a 0. Base of 1 is always going to give me, 1, 1, 1, 1, 1. And whatever base of negative 1 is, I don't need to generate that table. But all the other tables I need to generate. So if my prime number, right? So for mod 11, when you looked on Canvas, you got a, let's see if I can pull that up. What is this? This is quiz 8B. And it won't let me preview because it's got Proctorio on it. Bugger. Maybe I can do this and it'll let me see it. Sort of. Oh, wait. I can't preview the thing because it's got Proctorio on it. This is annoying me. It's one of those days. Okay, here it is. So if I look at this table, right? So these are all of the tables that needed to be redo, right? Here was the base 2. Here's the base 3. Here's the base 4. Here's the base 5. Here's the base 6, 7, 8, and 9. I don't need to generate 11 because 11, but I don't need to generate for base 10 because 10 is negative 1. So I'm going to cycle between 1 and 10, 1 and 10, 1 and 10. For 1, I'm just going to get 1, 1, 1, 1, 1, 1, 1. But for every number in between, I have to generate this table. So if instead of 11, I was using a really, really, really big prime number, this table, this massive thing that would have had to be generated would have been huge. Now, to compute, they don't need this, right? If they're going forward, they don't need all the tables. But to go backwards, you need the table. Okay? So that's kind of why this is secure. All right. So now Alice's secret number must have been 2 because 7 to the 2 was 11. I'm sorry, must have been 4 because 7 to the 4 mod 11 equals 3. Likewise, Bob's secret number was 2. Since I could do B equals 2, A equals 4. 7 squared mod 11 equals 5. Okay, so how do we feel about that 1 to 5? Okay. Now, the shared secret, right? The shared secret. Well, how do I figure that out? Well, let's look at it. The shared secret. Well, there are a couple ways to do it. I can take Bob, so I can do B to the A mod 11. Right? That was what B to the A mod 11 is what Alice computes. I can do big A to the little b mod 11. That's what Bob did. But notice, I'll just take this thing. A equaled G, which was a 7, to the, and that will get me the key. So both of these tactics will get me the key. But notice that A equaled G to the A. Right? That's how I found it, mod 11. So I could have done S would equal A to the B mod 11, which equals G to the A mod 11 to the B, which equals G to the AB mod 11. Right? So I could compute how Bob did it. I could compute it like Alice did it. Or, sorry, Alice did it. Or I could compute it like Bob did it. Or I could just compute it straight because I know both secret keys. Okay? So if I do it straight, this is going to be 7 to the AB, 4 times 2. Which equals, okay, well that's 7 to the 8. Which equals 9. Okay? So I could have done it that way. That's the clever way to do it. Or I could have just done it like Alice and Bob did. All right, so Alice's public that she sent was 3. So I could have done 3 to the squared mod 11, and that equals 9. Or I could have done this. This was B to the A. So that's 5 to the 4 mod 11. That's going to be 5 times 5 is 25. That's going to be 25 times 25 mod 11. And then what I'm going to do is, since 22 is divisible, I'm going to subtract 22. That's going to be 3 times 3 mod 11, which equals 9. So 25 equals 3. 25 mod 11 equals 3 mod, well, I'll just do the subtraction. So I subtract 11, and I get 14 mod 11. And then I subtract another 11, I get 3 mod 11. So I could have broken it up that way. All right. 1 to 5, how do we feel about that? Okay, so 7 to the 12th mod 11. Let's see, 12th is not on my thing. So that would have been the same as 7. So 7 to the 10th mod 11 is 1. Right? So I would have been left with a squaring. No. Oh, I see. No. So exponents don't do that. So yes, S is 9. So remember, exponents, you can't mod exponents because exponents have a different modulus than the base, than the field, the 11. The modulus works differently in exponentiation. So that was part of the point last time, was that you have to be careful with exponents. Now, addition and subtraction, I can do that. Okay, any questions about that? So yes, so in order to calculate the shared secret, you can't do 7 to the 6 times 2. I mean, you do that and then mod 11, but you can't mod the 12 in the exponent, okay? Because you get a different answer. Because the exponents don't work the same way that addition and multiplication does, okay? So what you would have to do, if your question was 7 to the 6, this was their question, 7 to the 6 times 2 is what I assume it was, mod 11, right? That's not the same as 7 to the 1 mod 11. This is true. But it's not the case that this is 7 to the 1. That's not equal. Okay? You can't mod the exponent. However, I can do stuff on this, right? So I know, for instance, that 7 to the 10, so 7 to the 12 equals 7 to the 2 plus 10. All right, so we'll put NZ11 here so I don't have to keep writing the thing, right? 7 to the 12 equals 7 to the 2 plus 10. And I know that, which equals 7 squared times 7 to the 10th. And I know on my chart that 7 to the 10th is 1. So that equals, since this equals 1, that equals 7 squared mod 11. And then I have to calculate out 49. Or I look at the chart, which tells me it's 5. So if I could pick off the number that equals 1, I can subtract, which is kind of part of what we're going to do today. Okay. Any other questions? All right. I have no quiz retakes will be up when I get them up. Please, it's test week for you. It's test week for Calc. Midterm grades are due, and I've got my own stuff that's also I got to finish. And the university's paying me for 40 hours a week. I'll give you all 50. After that, because I've got my own work I have to do too. So, you know, they and that sucks for you guys, but there's just some stuff that I'm not going to get to. There's just too much going on. But they will get up. They just won't get up right away. And Canvas doesn't let you do things well. It doesn't let you just duplicate a quiz. It lets you, but it only lets you do one at a time, and you have to be very careful when you do it. And it's rather annoying. So you can mess things up when you're importing quizzes. So it's tough. All right. So what we want to do. So is the stuff in this lecture going to be on the test? Okay. Well, everything on 8B on the quiz is on the test. That's fair game. Stuff today, what I'm going to do is I'm going to talk about exponents, and we're going to sort of talk about what we're going to do in Module 3, but I'm going to kind of finish off the exponent stuff. Is it directly on the test? No. Would it help you? You can do everything on the test without this stuff. Might it help you? Maybe a little. Okay? Just because you'll be able to apply some tricks. So let's just talk about what the big picture is for a moment. So the big picture of Module 3 is recursion. / induction. All right, so where are we going? We want to be able to we want to be able to do things with, we want to be able to prove things that are recursive relationships, and we want to be able to go down into stuff and pull up. And we want the connection. The big theme is that we want the connection between recursion in code and induction in math. All right, so that's the big theme of this. So what we're going to do a lot of the number theory you need for RSA. I don't know if we're going to make it to RSA or not. I want to, but we're going to be doing some of that. But in order to do that, we need recursion. Okay, so we need to be able to write recursive algorithms. Now, the thing about this, okay, why do we care? Okay, we care because we want to write programs that use recursive techniques. They're extremely powerful, and for some things, they're kind of the only way to get at the problem cleanly. But we want to be able to think of these in two different ways. And we're going to see this again when we look at regular expressions at the very end. There's kind of a math way to think of it, and then a code way to think of it. And the point is that these two things are really two sides of the same coin. And you can translate a problem from, from a recursive thing to a math thing, work on it, and then use that to translate it back. So there's some problems that are easier to think about in terms of mathematical induction. And there are problems that are easier to think of in terms of computer recursion. All right. And the point is that if you can think of one in one way, you can think of it in the other way. Okay. So there's a point. Now, the big things we want to show. All right. These are the big kind of goals. We want to show there are things that computers can't do. Okay, basically. So we want to show that there are that you can't enumerate the real numbers. Other things I want to show. I want to show there are things that are true that cannot be proven. And I want to show there are questions that a computer cannot decide. Right? So there are things that, right? There are things I can't even list. All right? Or there are things I can't even write a program that would get there if I gave it infinite amount of time. There are things that, so there are things I can't enumerate over. There are things that I cannot, that are true that I can't prove. This is, and then there are things that I can't decide. So things like whether or not I'm stuck in a loop is not something that a computer can actually know. I can't write an algorithm to find out if my computer is stuck in a loop. I can't write with, that's decided, right? I can write ones that say, oh, ping it, and if it's not 20 seconds, we'll assume it's out. It's stuck in a loop for infinity. But you're making it's not an actually deciding whether or not it's stuck in a loop. It's just like saying, 20 seconds was long enough. I want to show that this is Gödel's incompleteness theorem. This right here is, I want to say it's Dedekind's theorem. I'm not sure about that. I have to look it up. I have to do it on a day when I'm not like other people are yelling at me. Okay. So these are kind of the long-term goals. All right, and then I'd like some number theory. I would like the number theory needed for RSA. Okay, so the first of these things that we're going to talk about is the exponents. Okay, so how do we feel about what's about to happen 1 to 5? These buzzwords that you guys know or not? You don't know what's going on. Okay. So let's start with like some exponent tricks. And then we're going to have our first, we need to set up the recursion to do the extended Euclidean algorithm. So RSA is the security thing where you share certificates and stuff like that. All right, so that's the big picture about what's going on. Let's do some exponent tricks first. Okay, the first of these is I can go backwards. Okay, so in other words, consider 10. Okay, so let's do Z11. So examples will all be in Z11. Okay, I can go backwards on the base. So in Z11, here's an example of that. 10 to the 100 equals what? Somebody do 10 to the 100 mod 11. Right? Example in Z11. Well, exactly. What? But remember that 11, right? Somebody's got it already, right? 10 is equal to -1. And -1 to the 100, that's an easy thing to do. I've got an even exponent. That's going to be 1. Likewise, 10 to the 99 is going to be -1 to the 99. That's going to equal -1, which equals 10. How do we feel about that 1 to 5? I know -1 to the 99 is -1 because it's -1, right? It's going to go -1 times -1 is 1, times -1 is -1 again, times -1 is 1. So every time anytime I have an odd exponent, I wind up at -1 again. And every time I have an even exponent, I wind up at 1. Okay. Two, I can add exponents. Okay. So recall that A so I'll do x. Recall that x to the a times x to the b equals x to the a times b. Okay? So if I have 7 to the 12th in mod 11, right? Now, I already knew that, right, that's off that chart I had. But recall on my chart, 7 to the 10 equals 1. So if I have 1, I can figure this one out, right? If 7 to the 10 equals 1, that's 7 to the 10 times, this is 12 equals 7 to the 10 plus 2, which equals 7 to the 10 times 7 to the 2. Right? And I know that 7 to the 10 is 1. So I've got 1 times 7 to the 2. And now I have to figure out what 7 times 7 is. Right? That's going to be annoying in mod 11, but I can do it. It's 49, right? 7 times 7 equals 49, which equals, I subtract 11. All right, so my brain's not working here. 38. I subtract 11 again, and I get 27. I subtract 11 again, and I get 16. I subtract 11 again, and I wind up with 5. Okay? 10 equals negative 1 because we're dealing in mod 11. So I go back 1 instead of going forward. So if I take negative 1 and I add 11, I get 10. Or if I take 10 and subtract 11, I get negative 1. So that's below you. So I can do these things. Also note, this gives me an easy way to figure out what 4 was, right? So 7 to the 4th equals 7 squared times 7 squared, right? I've got 7 to the 4th equals 7 squared times 7 squared equals 5 times 5 equals 25. And now I do some subtraction. 25 equals, 14 equals 3. How do we feel about those tricks 1 to 5? Someone's asking if this material from this lecture is going to be on the exam. The answer is only on yours. There's now a special exam that will have this material, and it's yours. I had a professor that I always liked this from now on, right? I had a professor that said, every time you ask me if something's going to be on an exam, the answer just became yes. Right? So every time you asked it, hey, is this going to be on the test? It is now. I like that. Oh, and remember I can subtract as well. It should be a plus, not a times. Okay. The next thing I could do is I could do strange things with exponents. Okay? So the next thing I could do is I can multiply exponents. Okay, so x to the a to the b equals x to the ab. right? And this is the trick that RSA, that Diffie-Hellman uses. Now, why is that useful? That's useful because if I can get my base to be -1 or 1, that, is easy to compute. Okay? How do we feel about that 1 to 5? I can change my base by using this trick. All right, so let's give an example. Let me pull back up the, let's see, which one was -1? So, for example, suppose I want to do 7 to the 25, again, mod 11. So I want to do 7 to the, let's not do 25. Let's do, 7 to the 25. Mod 11. Now, I know that 7 to the 5th equals 10, which equals -1. Okay? That was on the chart in the quiz, if you don't believe me. Just flip back to it real fast. Okay? Okay, so using this trick, I would have found it the next time, right? I just did 7 to the 4th. That was 3. I would have done 3 times 7 again, and I would have found that that's 10 when I was all said and done. Okay, so 7 to the 25th equals, well, this exponent here, I can make this exponent 5 times 5. Okay, so I can factor the exponent. All right, well, that means that this happens. Right, when I factor the exponent, I use the rule x to the AB equals x to the AB. And I wind up 7 to the 5th is -1. And then I do -1 to the 5th, and I wind up with -1, which was 10. How do we feel about that 1 to 5? So that's this idea. If I can figure out that what I've got is a multiple of 5, I can do it. So the -1 comes in because 7 to the 5th equals 10, and 10 equals -1. So what I have here, I'll just erase this and do it real fast. This 7 to the 5th to the 5 is 10 to the 5th. But 10 equals -1. And then I've got an odd exponent, it just goes up. That's a pretty slick trick to have in your pocket, right? All right. Let's look at the binomial theorem. This is the binomial theorem with mod. So still in Z11 is going to be our example, right? So let's do this. I do A plus B to the N mod K equals, well, this is going to be A plus B A plus B, 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 right? And each one of those I can mod first. So I can mod A plus K before I do an exponent. But that's the same thing as A mod K plus B mod K to the n. This has some big consequences. If K divides B, I'm going to only have pieces of it left. All right, so look at what's going to happen. I wind up with A plus B, so in mod K, I wind up with A plus B to the n equaling A plus 0 to the n equaling n. I'm sorry, equaling A to the n. Now, so let's go back to mod 11. Still in Z11. All right. I have the number 22 to the 25. Now, I can break this up. Oh, that's easy because that's 0 to the 11. Let's do this. Let's do 23 to the 25. So I can break this up to be 22 plus 1 to the 25, and that's going to equal 1 to the 25th, because this right here equals 0. How do we feel about that 1 to 5? Okay. Yeah, that's boring. Here's a really sick one. Assume K divides A times B. Then A plus B to the n equals A to the n plus B to the n. Right? This is called the freshman's dream, by the way, because math instructors want to associate you. 22 is 0 because I'm in mod 11. So 22, so 11 times 2 is 22, right? Subtract 11 twice and you wind up at 0. This, by the way, is called the freshman's dream. That is actually the name of the theorem. I am not making that up. I am not saying bad things about you that are freshmen. I'm saying that's the name of that damn theorem. If K divides A times B, then obviously everything mod K, A plus B to the n equals A to the n plus B to the n. Why is that true? Let's prove that fact. All right, A plus B to the n equals A choose 0, A to the 0, B to the n, plus A choose 1, A to the first, B to the n minus 1. Sorry, this should be n's, I'm sorry. not a's, n's. There we go. Plus n choose 2, a squared, b to the n minus 2, plus dot, 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 plus n choose n minus 1, a to the n minus 1, b to the first, plus n choose n, a to the n, b to the 0. Okay? Now, since a divides ab, sorry, since k divides, what did I say? Yeah, since k divides ab, what's true? Goodbye, 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 and the only thing I'm left with are the 2 at the end. Okay? So I'm left with b to the n plus a to the n. Right? Here it is, right? I expand using the binomial theorem. And since k divides all of these terms, and remember we're dealing with we are in zk. So since k divides every term in the middle, all I'm left with are the 2 terms at the end. Right? Because this has an AB in it. This has an AB in it. This has an AB in it. The only thing that doesn't have an AB in it is this term and this term. Now, that's not very useful if k is prime, but it's extremely useful if k is not prime. Indeed, RSA is going to exploit this fact. How do we feel about that, 1 to 5? So all I did was divide out the pieces that were in the middle. I mean, all I did was mod out the pieces in the middle. All of the pieces in the middle, right? Since k divides AB, this has an AB, this has an AB, this has an AB, this has an AB. Well, that was the thing. Assume k divides AB. All right, that was the thing. This only works if k divides AB. All right. Let's do an example. I'm going to let k, it only makes sense. It's only useful if k is not prime here. So let's do k equal 15. Nah, it's going to be, yeah. So I'm going to look at 9. And 5. All right, so I'm going to look at 9 plus 5 to the to the 10th, or whatever. I don't actually care. All right, now, the point here is I've got 15 here, I've got 9 here, and I got 5 here. Notice that every term in the middle, 15 divides 9 times 5, right? 9 times 5 is 45. That means 15 will divide. It's not, k doesn't have to be not prime, okay? We only care about it. If k is prime, that means that either B or A divide. So we go up to here, right? We use this trick, right? So we get rid of the, we just get, if A is, if K is prime, one of these numbers will divide, what am I trying to say? Yeah. So if K is prime and B and K divides AB, then K divides A or K divides B, right? That's part of being prime. But if K is not prime, then I've got something interesting. Okay. Then I've got something useful. I mean, it's still useful. It's still true if K is not prime, but I can use this one up here if K is not prime. However, if K is prime, I can use this one because that means that K divided A or K divided B. Now, here's why this is useful, right? 9 plus 5. Well, everything in the middle, right? So let's look at it. Let's go. Right? So let's look at the stuff in the middle. 9 plus 5, let's do 9 plus 5 cubed. Let's do something that's not going to give like a ton of terms, right? But at least gives more than 2's, right? So if I expand this using the binomial theorem, I'm going to get 9 cubed plus 9 squared. I'm sorry, this should be 3, choose 1. 9 squared 5 to the first, plus 3, choose 2, 9 to the first, 5 squared, plus 3, choose 1, it should be 3, choose 3, 3, choose 3, 5 cubed, which is just 5 cubed. So I'll just write it like that. Okay, now 15, this number 15, which equals 5 times 3, divides 9 squared times 5. This number here, 15, divides 9 to the first 5 squared. So these terms are both 0. And all I'm left with is 9 cubed plus 5 cubed. Okay. How do we feel about that now 1 to 5? All right. And there's one more. And this one's called Fermat's little theorem. So this would be number 5. This one has a name. It's called Fermat's little theorem. All right. And Fermat's little theorem says the following. Let P be prime. Okay. Then in ZP, okay, and A not equal 0, by the way. and a not equal 0. In ZP, a to the p minus 1 equals 1. Okay, so that means here, the examples here for Fermat's little theorem. All right, example. Z11. 5 to the 10th equals 1. 8 to the 10 equals 1. 7 to the 10 equals 1. Okay. That's Fermat's little theorem, and it's extremely helpful when combined with these rules here. Because remember that if I can get this to be something like 1, I'm done, right? Or if I could break up things, right? I could break up things, I could divide things. I'm focusing on Z11 because it's not Z11 is kind of one of the first ones that actually has some structure to it, right? Because if you go for the small primes like Z2, Z3, Z2 is extremely boring. Z3, Z4, Z4 is not prime, but Z5, Z7, all of these small things, they have additional structure based on the fact that they're really small. While Z11 has enough stuff in it that you get like multiple things going on, right? Because you've got, because 10 has 2 prime divisors. So the multiplicative things, you have some that cycle over 2, some that cycle over 1, and some that cycle over 5, and some that cycle over 10. And it's the first one that's really interesting to play with, right? It's the first one where you can make things happen. But you can do Z13, that's a good one too. But 12, right, we can go bigger. No, Fermat theorems hold true for any z where z is prime. So, for example, again, in Z13, 5 to the 12 equals 1. 7 to the 12 equals 1. Okay? But the point is I can mix and match these, right? So suppose I want to compute in Z17, all right? I want to compute z to the 18 is just 1. Let's say I want to compute z to the 6. So let's say I want to compute 5 to the 16. Okay? I claim I can do this by figuring out what 1/5 is. Okay? 5 to the 16. Well, I can break this up by doing, there are a couple things I can do. I can do 5 squared and then do another number here. But look what else I could do. I can do, if I had, 5 to the 16th is just 1. That's boring. Sorry, that'll be 1. Let's consider 5 to the 15. All right? That's going to be the same as 5 to the 16 times 5 to the negative 1. Okay? And that's another trick I should have put up here. I can do negative exponents too. 5 to the 16 times 5 to the negative 1. I know that this is 1 by Fermat's little theorem. So I only need to figure out what the inverse of 5 is 17. So what is 1/5? Okay, well, 1/5 is 5 times is x, so that x times 5 equals 1. Okay, so what am I going to do here? Well, 2 is 10. That ain't going to do it. 3 is, what about 3? So let's see. 3 times 5 equals 15. Not there yet. But 3 times 5 equals, yeah, that's not going to help. So 3 times 5 is 15 is negative 2. That's not going to help. Let's do it again. 4 times 5 is 20. Um, 20 minus 17 is 3. That's not it. I'm looking for 5, right? I'm sorry, I'm looking for 1. Let's see. 5 times brain. 5 times 5 equals what? That's 25. 25 is, I could just add 17 to that. That's I'm sorry, I can't do that. My brain's not working. I can just add 5 to this. I'm going to wind up with 8. 6 times 5 equals, add another 5 to that. I'm going to get what? 7 times 5. So add 10 to that equals 18 equals 1. So there's the one I want, right? But that means here that this is 1, 5 to the negative 1, right? So 1/5 equals 7. So 5 to the negative 1 is 7. So this equals 7. So this is actually fairly powerful. I can get at things using this trick. Because 5 to the 15 is 5 to the 16 times 5 to the negative 1. Especially if I know some of this information ahead of time, which is possible. Okay, any questions about that? So Fermat's little theorem only works when P is prime. Okay, so next time we're going to prove Fermat's, I think we proved Fermat's little theorem. I think we're going to prove Fermat's little theorem next time. I'll check the list. Okay, so next time we're going to start digging into recursion and prove some of these things. There's also some proof cleanup we need to do. So we need to clean up the fact that we need to clean up to the fact we never proved that there are an infinite number of primes. We need to do that, and there's some other things that we just have to clean up as well. And we need to do pigeonhole and stuff, right? Yeah. So 5 to the negative 1 was 1/5. Right, because if you think about it, 5 to the 15th equals 5 to the 16th times 1/5. So if I could figure out what 1/5 is, I could solve that problem without having to go keep multiplying and multiplying and multiplying. Because I know that 17 is prime, and I've got, I can make 5 to the 15th be 5 to the 16th times negative 1, times 5 to the negative 1. Any other questions? And by the way, if you're in calculus, don't confuse yourself. Fermat's theorem in calculus, something totally different. There are a lot of Fermat's got a lot of things named after him, so watch out. This is Fermat's little theorem. Any other questions? Okay, well, that's it for me today. Reminder, test is tomorrow at 12:30. You need to log into Discord. Anything else? The test review to YouTube, I can do that. If I have time, I will upload the test review to YouTube. It is on Twitch, though. Anything else? Okay. Well, that's it for me then. Bye.